Hi, I'm Rob, and the main focus of my PhD is the mathematics of electron microscopy. Over the next few minutes, we're going to give you a quick introduction as to why we use electron microscopy and how this relates to mathematics. So the first question to ask is why electrons? And the biggest advantage of an electron over visible light microscopy is resolution. On the right, we see a picture of an ice crystal, and we could just keep zooming in to whatever magnification we want. With visible light, you have to stop at some point. It's called the diffraction limit. We just can't keep zooming in forever, but with electrons, we can go much further. Another reason why electrons are great is that they interact with matter a lot more than photons. If we look at this colourful picture in the middle, then we can start to see this. If you just want the physical structure, then we have these grayscale images at the bottom. But on top of this, every bounded atom gives off a characteristic signal, and so we can identify exactly which atoms are where. And in this case, we can see that there's silicon on the outside and titanium on the inside. And this is something else that you just wouldn't get with other types of microscopy. The result of all of this is tons of new discoveries in science. I remember in my physics A level we were taught a lot about properties of metals like atomic dislocations and how doping changes conductivity. These all come back down to electron microscopy. Either you look down the microscope and you see something you weren't expecting, or you have a theory but can't test it until you see it. The final image just shows that these techniques are also used in medical fields as well. Here we're looking at an HIV virus, and in particular we're seeing antibodies bind to its surface. Actually being able to see these objects and their structure in 3D, people were hoping that they could go away and design better and more targeted drugs. Okay, so the final thing that singles out electron microscopy is that we can do full volume reconstructions, and this is where the maths comes in. If you think of a photograph, then you only ever see the surface of an object, but electron images are much more like an X-ray where you see all the way through an object. But getting 3D reconstructions from 2D pictures is hard for exactly the same reason that the picture on the right looks so funny to us. We have a 2D image, but a lot of important information is stored in the third direction that we can't see. How we overcome this problem is an interesting mathematical problem, and the sorts of things we ask are, can we do better with the data that we've been given, or can we get the same quality reconstruction but from less data? There are three main things that we look at here. So the first is how to model the physics of the problem. Unfortunately, the interactions that happen when you fire an electron at an object are very complex. There are elastic interactions, inelastic, there are diffraction, there are radiation emissions. We just can't model them all. So normally we resort to a much more basic model, but if we could use a better model, then we would get better reconstructions. The methods we use most often are what are called priors, and this is exactly what we internally use when we look at this picture. Our eyes tell us that it's a two-headed rhino, but our prior knowledge tells us that two-headed rhinos do not exist. So it must be just two rhinos with one in front of the other. More generally, priors simply encourage good features in reconstructions. For instance, when you look at this image, when there's the transition from ground to rhino, then it's a very sharp transition. The ground is very light, the rhino is very dark, and the interface between them is just a jump. One pixel is light and the next pixel is dark. The challenge is how to represent these verbal priors numerically so it can be fed into the reconstruction process. Finally, the actual algorithms that we use. Scientists who want to use these techniques always want them to be as quick and efficient as possible. So this is another area of mathematical interest, to design ever faster algorithms for the same class of problems. So as I've just said, the difficult part is inverting 2D images to get 3D reconstructions. Unfortunately, these are quite difficult to draw as well, so I'm going to talk through the process of getting 2D reconstructions from a series of 1D images. Now the forward process is quite simple to explain. I send a load of electrons through my sample, and if there is something heavy in the way, then it's likely that the electron gets deflected or absorbed, and these correspond to bright patches on my projections. Otherwise, if there is nothing in the way, then the electrons pass straight through, and this will look dark on my 1D image. I repeat this for a number of different rotations and stick all of these images together to give me what's known as the sinogram at the bottom here. Now the process of reconstruction is exactly the problem of calculating the right-hand image given the raw sinogram from the electron microscope. Studying the relationships between a sample and its sinogram is really at the heart of the mathematical process here. Trying to identify how useful features in a sample are represented on a sinogram is hopefully how we can improve methods in the future. Hopefully the fact that the sinogram looks so different from the desired output will convince you this is a non-trivial and actually quite an interesting mathematical problem to work on. The problem with all of this in practice is you never see the perfect sinogram. It might be very pixelated, or stochastic processes will add noise to the projections, or sometimes data is just missing. The idea of missing data is really common in practice, and one of the ways that it arises is that sample holders are not capable of rotating the sample all the way around. You can rotate a bit to the left and a bit to the right, but only to a limited degree. And this is the example I'm showing off to the right here, and the results of algorithms applied to this data can be seen below. Now, looking down to these bottom images, we see how algorithms have developed through time. Now, right back in the dawn of electron microscopy, people used to use something called filtered back projection. It's a very quick method and is exact if you've been given a perfect sinogram, but there are many cases when this does very badly in practice. Moving on to the 70s, we get the CERT algorithm. In this example, it doesn't look much different from the filtered back projection, but in general, it's a lot more robust to dodgy data. If you have a small amount of noise in your projections, then this has a small effect on the quality of your reconstruction, as you'd expect. These days, we've started using total variation-based methods, and these are exactly the prior methods that I mentioned earlier. So here we have the prior that different regions have sharp boundaries between them, and in this case, the reconstruction is perfect. But this is just one example. There is much more to do, but in general, this reflects the natural progression from fast but unstable methods towards slower but much more robust algorithms. Anyway, I'll leave you with references for the images that I've used in this video, and if you're interested in knowing more about them, then here's where to go. Other than that, I hope you've enjoyed the video, and thank you for watching.